Everyone, my name is Hanoi, and I'm a double major in applied physics and music, and I'm a senior. And today I'll be presenting on my project in applied physics, which combines my passion for music and applied physics together. And I brought in the prototype of what I'm working on right now to give a short demonstration. And its current iteration looks something like this. So I'll just And to give you a sense of what's happening, if I remove all of this, then the sound that you're going to get is actually just this little thing here. And
the violin is serving as a sounding board.
Yes, so that is the title of my presentation. So the project that I'm working on, here we go, just put this in. There's the, and yeah, there's a little slide there. There you go, slide. Ooh, everything's been switched. That's okay. And the clicker. Do you have a clicker? It's fine. Cool. So my project is, as you're guessing, has something to do with soundboards. So it's surrogate soundboards for novel transmission of instrumental audio. And what got me motivated to start working on this project is Yale is one of the best places in the world to be studying and to be both experiencing music. And I can definitely attest to that, being a music major here. And what I was thinking was, well, it's great that I'm here, but what about my friends back home in Thailand? How can I share this music with my friends back home in Thailand? How can I share this music that's happening at Yale with the rest of the world? And probably what you'll tell me to do is to log on to the Yale School of Music website, and the Yale School of Music streams all their concerts from Sprague Hall and televises it online live. And this is how my parents kind of keep up with some of the concerts that I play with when they want to tune in from Thailand. And this is where the problem starts. Because when we listen to this concert through the online stream, we're going to be listening it through maybe some kind of sound system, or our computer speakers, or our headphones. And this is where the problem starts. So let's have a show of hands. How many of you agree with me that listening to a recording of an instrument never sounds the same as listening to the instrument being played live in front of you?
I wouldn't say never, pretty close.
Pretty close, okay, but it's never quite the same. And that is mainly due to the fact that you're listening to the sound through speakers. And the way that speakers work are very, very different to the way that an instrument body, an instrument soundboard works. So a speaker works by having a woofer, a cone that moves in and out like this and causes vibrations in the air. So let's contrast that with the way that a violin works. So it turns out that the wooden body of the violin has very complex and also very specific patterns of vibrations. And when you sprinkle a little bit of baking soda or some kind of powder onto the surface and you get the violin to vibrate, the powder will start to accumulate in nodes on the surface. And nodes simply refer to parts of the surface that remain stationary. And you can get an even better sense of what's happening on the surface of the instrument using a system like interference holography. And you can see here there are systems of nodes and antinodes. So different parts of the violin are moving up and down, and others are remaining constant in some of these very, very beautiful patterns. And what happens when you have systems of nodes and antinodes is they behave kind of like point sources. And when you have 2 point sources, you get constructive and destructive interference. And that this interference pattern becomes a lot more pronounced at higher frequencies. Which means that higher frequencies emanating from the violin are very, very directional. The directivity of the higher frequencies is very important. So as you can see down there, at 3,300 hertz, which is sort of at the top end of the violin, the spectrum that the violin produces, you see a lot of sharp spikes, and that's a result of the interference patterns that occur at higher frequencies. And if you look at the lower frequencies tend to emanate in all directions. So directivity becomes increasingly important when you move to higher frequencies. And this is summarized in this diagram here. So you notice that the higher frequencies from 2 to 5 kilohertz tend to only come out from the front of the instrument, while lower frequencies from 200 to 500 hertz, the big red circle there, tends to be more omnidirectional. And the thing that I wanted to get you guys to appreciate is the fact that, yes, a speaker will have its own pattern in which it radiates these different frequencies, but there's no way that this simple one cone system will be able to reproduce the complicated directional pattern of frequencies that it's emanating from the violin. And this is the principal reason why listening to an instrument live sounds very different to listening to it on a speaker. Although the frequency content might be the same, the way the sound is being projected in these different directions from an instrument body versus a speaker is completely different. So, for example, here with the violin, you have the low frequencies bouncing around the room and then arriving at the listener's ear. Whereas in a speaker, you kind of have everything being thrown at the listener in the forward-facing direction of the speaker. So my idea was, well, is there a way we can combine the best of both worlds? Is there a way that we can preserve the acoustic and mechanical behavior of the violin to preserve all its complicated and very beautiful patterns of vibration, but still retain the connectivity of a speaker system and the benefits of the sort of digital electronic audio world? And so my hypothesis was we can think of the violin body as a system that takes an input and an output. It takes the input from the strings, and then that causes a vibration to the bridge. The bridge vibrates, then transmits this vibration down to the body of the instrument, and then the body of the instrument vibrates. And then the body sends out the sound that we perceive to be the sound of the violin. The body has no idea what kind of vibration is causing it to vibrate at those 2 points there where the feet of the bridge touch the body of the instrument. So my hypothesis was, well, as long as I get the vibration at that spot identical to how a real violin works, the body of the instrument should respond in the same way, as long as I introduce the same vibrations. And I think those two locations there, which is what I've tried to do in my first prototype, where instead of having the strings, I replace it with an actuator that's clamped onto the bridge of the instrument and moves the bridge up and down. And the signal that I take to drive this actuator is a signal that's taken from a live violin. So however the bridge is moving up and down on a real violinist I'm getting the actuator to move the bridge of this instrument up and down in the exact same way to see if the body sounds the same. And you guys had a little, I wouldn't say taste, a little ear taste of how that sounded like. And so the physics, the reason that I think that we're able to do this is by looking at the physics of how the instrument works. So as I alluded to before, the violin can be thought of as a system with an input and an output. So you first start off with the vibrating string, and this is what a vibrating string looks like when it's being bowed. So in slow motion, you see that there is a kink that's moving back and forth, which is very different to a string when it's being plucked. The string when it's being plucked is composed of looks a lot more sinusoidal, but here you get this kink that's moving back and forth. It's called the Helmholtz kink, because Helmholtz was the guy who discovered it. But the effect of that is the signal that you get out of a bowed string is actually a sawtooth wave. So the string that's currently being bowed applies a force onto the bridge at that contact spot with a signal that varies like a sawtooth wave. And sawtooth waves are signals that contain a lot of high frequencies, which is shown in the graph below there, where you have a lot of frequencies in the higher ranges. What then happens is the bridge then takes the signal and changes a vibration that happens in this plane, which is the plane at which you're bowing, and then changes it so that the vibrations happen in this plane. But the bridge also has its own frequency response. And what I mean by frequency response is that the bridge will amplify and it will deaden certain frequencies. So, for example, here, the bridge has two peaks at around 500 hertz, and it also has another peak at around 3000 hertz, but a dip everywhere below that, so it will actually filter that sawtooth signal with its own frequency response. Then we get to the body, and the body of the violin also has its own frequency response and will further filter the sawtooth wave, and then the final result that you get is the sound of the violin. So it's this sort of step between getting the source signal from the string, sawtooth wave, filter through the bridge, filter through the body, and then you get the output waveform. So the way that I've tried to approach this problem is by kind of thinking that if I just hack the instrument and hack into the signal path at the correct spot, the violin should have no idea sort of that, oh, well, it's not a string that's vibrating me anymore. As long as I get the same vibration, I'm just going to behave the same way. So the idea would be we have the live violinist, and we take the signal from the bridge of the live violinist, and then we actuate the surrogate instrument, we actuate the bridge in the exact same way. And this is the current prototype here that uses that idea. And sort of my dream of where this would go, it would allow you to stream concerts simultaneously across the world to sort of surrogate orchestras or surrogate string quartets located around the world. And it's sort of in this interesting space between sort of streaming a concert and actually going to see it live. This kind of sits in this interesting gray space between, and it also raises a lot of interesting questions on what actually is a live musical performance, because we can get the acoustics right, but then if there's no people there, is it a live performance? And so that's some of the things that I'm interested in. So here are some of the preliminary data that I've been working with. So this is the signal that I take from the bridge of a live violinist. This is what the signal looks like. You can see that it looks like a sawtooth, but it's kind of a little wonky because it's been filtered through the bridge of the instrument. And then when I actuate that signal onto my system and then I take the measurement at the same point, this is what the signal looks like. And you can see that the waveforms look very different, which is what I expected, because this is a new system which has its own frequency response, it has its own characteristics, which are currently intruding into the way that a normal violin works. If the two signals were exactly the same, that would be very weird. So what I'm currently working on now is finding the transfer function that will sit in between the signal path, so that when the signal that I take from the live violinist goes through this transfer function, which would exist on my computer, and comes back here, if I take the same readings from the same location on both instruments, they should look identical, and I can say that mechanically the same vibrations are being introduced into the body of the instrument. You can get the same, when we look at the frequency, the power spectrum, so this is frequency on the bottom and the amplitude on the top. It's the same information as what I just showed you before, but just shown in terms of frequency and amplitude. This is what the real violinist, the spectrum from the bridge, looks like. And then when it passes through into my system, we see that certain frequencies are being changed. So we see that the fundamental kind of stayed where it was, but then all these higher frequencies are being deadened out. And so my job is to characterize exactly how the system is operating so that I can introduce what's called a transfer function that functions as an inverse filter and basically changes the signal so that when it arrives here, it's as though this system never existed, and that it will just function like the original. Violin. Also, the second design that I'm working on will feature two independently actuated feet, and this is doing some prototyping here. It's right here. So, actually, what happens is the bridge of the violin. It's a very fascinating piece of engineering. it's a little bit like natural selection, where this design has been arrived at over centuries and centuries of just trial and error. But when you do like physics analysis on it, it's like, oh, cool, it works exactly the way it needs to be. And the violin makers, Stradivarius, had no idea of the physics going on, but they were just doing it through trial and error. And it's almost like natural selection, but for musical instruments. There's an interesting article where they use the same word of natural selection in the evolution of musical instruments. But it turns out that the 2 feet are actually able to vibrate independently of each other. So you have a mode where both feet are moving up and down at the same time. You have a mode where only the right feet is moving up and down, a mode of vibration where the left feet is moving up and down, and a mode of vibration where both feet are kind of moving out of phase from one another. So to take that into account, I've been thinking of ways to actuate these 2 feet independently. So this is just a very rough 3D print of a bridge with two independent actuators and some little 3D printed feet that mimic the shape of the bridge and body interface. And the reason that it's a little bit fat is because I'm also trying to figure out ways of integrating this whole setup, the electronics and the signal processing that occurs on my computer, into some kind of embedded chip, an embedded system that you would just literally place onto the surrogate soundboard. So applications. So we alluded to some applications. We can have, allow a new breed of teleconcerts for string quartets and for orchestras. And we can also do a 1-person string section, because you could just send the same signal to 20 or so different surrogate soundboards, which might unsettle a lot of violin players and put them out of jobs. But as I always say, I'm a pianist. It doesn't bother me. There's one of me anyway.
Let's hit the symphony.
Wouldn't it sound bad though?
I don't know. That's I think that's
there's a lot of aesthetics in the lack of micro coordinate, the variations.
Yeah, but the interesting thing is, once I have the signal from the live instrument, the 20 signals or so that I'm sending out, I can introduce little micro variations in between those that simulate different people playing. So I can have this person be slightly out of time, this person arrive on the note a little bit earlier, just like a real musician would.
Instead of Cleveland, Vienna, Bond House, and add the house style.
Yeah. So that is something that I'm very interested in, and right now I'm just sort of being limited to just one instrument soundbook. But it would be a fascinating thing to actually apply this to a whole symphony of instruments and see what the sound is like, and do blind tests to see if people can perceive differences in the live performance. I think it's also interesting in terms of for the recording industry, because if you simply record the source signal from the bridge of the instrument before it goes into the body, then you can play that back into the body of the instrument as many times as you want, and change the microphone placement as many times as you want, without having to employ the violinist for a whole month of recording, which is also bad for violinists, but good for audio engineers like me. And in the music domain, in the compositional world, there's been a lot of interest in new sound systems that go beyond speakers. So there are speakers in different arrangements, for example, in hemispheres, in full spheres, and I think that having a sound system that actually imitates and breathes like a real instrument, I think will open a lot of interesting compositional platform for composers who want to write electroacoustic music. But instead of having sound come out from speakers, they actually have sound come out from surrogate instruments that behave and respond like real instruments, and explore the interesting soundscapes that would arise from the interaction between surrogate soundboards and real musicians. Okay, well. So this project wouldn't have been possible without my advisor, electrical engineer, Professor Roman Kutz, Professor Larry Violin in the CID, who helped me with all the machining and sort of the mechanical implementation of this project, and also the Franke Fellowship, which provided pretty much all the funding to acquire all these like little gizmos and gadgets. Here we go. Where to next? So what I'm working on this semester is figuring out that transfer function and that inverse filter. And me and Professor Kutz are trying to figure out is we have information, when you're working in the signal domain, you need to know the amplitude response, the frequency response, sorry, and the phase response. And right now, I'm able to pick up the phase of the amplitude response, which is what I just showed you, but I have no idea about the phase. And in order to characterize the system, I need to know how the system also tampers with the phase of the signal. And it's about figuring out exactly how this phase works. And why is phase important? Well, if you play the violin backwards, you know that the sound of the violin is being played backwards. So phase is important. And so there's a relationship called the Kramer-Kronig relationship, which basically allows you to derive one quantity from the other. And Professor Kutz, in a paper in 1984, showed that in particular systems that are defined as causal, but in special kinds of systems, you will be able to derive the phase of the system, knowing certain things about the frequency response. So we're investigating if we can apply the same thing that he showed in 1984 in a paper to do with tissue and to do with frequency response of tissue to this particular system, and seeing how that will work. And where to next in terms of, I guess, what I'm doing. So some good news. I was recently accepted into the Karma program at Stanford, which is the Center for Computer Research in Music and Acoustics. And this project was sort of like one of my spearhead projects that I use in my applications to grad school. So thank you very much to the Franke Fellowship for making that possible. I'm waiting to hear back from the MIT Media Lab, but they also have really cool integration of physics, music, electrical engineering, all the technical disciplines of music. And I'm really excited because I got to work there over the summer, and I really want to go there. Yes. And also I'm also thinking of taking a gap year too, depending on how all the graduate applications go out. I also really want to go back home and spend an extended period of time with my family. I'm an international student from Thailand, and I only get to go back twice a year, but each time I go home, it's about for a month or two, and it would be nice to go back and just spend, a nice 6-7 months with family back home. So those things are kind of floating around in the works right now. But yeah, thank you very much. Yes.
So is the phase relationship, is that changing dynamically, or is that part of the fundamental way in which the bridge takes input?
Yes.
And is it just one characteristic function, or
yes. So
with every aspect of it?
Yeah, so basically we need to be able, so the phase response is a function of basically, so the phase response will look like that, and it will stay like that for the entire duration that the system is in.
So is that possible to characterize then with structured input to a bridge on your original instrument,
mm-hmm.
to test it and discover this rather than computationally? You input at this point on the bridge a certain frequency.
Oh, I see.
And you change it. You move it to here, and you take all of that input and essentially just.
Yes.
By having a very, very pure source.
Yes. I see.
The variation that comes out of those is going to be a result of the phase interactions.
True. That kind of testing that you've just outlined is a very well documented kind of testing, and it's called, you send in what's called an impulse response into the system, and you measure its impulse response. And once you know the impulse response of a system, I can tell you the phase and the magnitude relationship.
Right, because it's pure, so any variation that comes out is going to be.
So an impulse response just basically contains all the frequencies, and you're literally just sending in 20 to 20,000 hertz, and then you measure what comes out, and then you know that if I send in 20 hertz and it's like at 5 decibels, and then it comes out at -3, then I know that the frequency response at that is -8. The difficulty comes in how do you apply that impulse response. In the case of when the data that I showed you for the impulse response of a bridge, the way that they do it is actually really complicated, but what they do is they put a laser here, and then they have like this really small lever that kind of like comes on and like swings around and knocks onto the violin, and then that delivers the impulse. And then they use the laser and this little mirror that reflects off of it. They use that to measure the impulse response of the the bridge of the
Yeah,
instrument.
we've done that with bird feathers.
Oh, cool. Yeah. But that is number one, very complicated to set up, and actually Yale doesn't have Yale doesn't not have the acoustics gear to carry that out. Number two, it would also so that's a very that's a kind of testing that only dedicated like acoustics labs are able to carry out. So characterizing my system in this way, although it would lead to the answer, is I'm not able to do it in that way. So we're trying to use this sort of...
Well, if you do the computation, then it'll apply to any, and you figure out how to, then it'll apply to any instrument system equally. But this would, you'd have to start with another violin, you'd have to redo this.
Yeah, and also, right now we're currently working with different iterations of how we're going to design the new bridge. And so, to figure out the frequency response, if let's say we just change the design of the bridge, we would have to figure out the whole, like how to measure the frequency response all over again. But approaching it this way, I can change the design as many times as I want, and still have a way, still have a way of
to make this correction.
To make the corrections, and account for any changes to the signal. Yes.
It strikes me that what inspired the project is this discrepancy between your experience in a live concert and your experience hearing it, whether it's streaming live or recording. And I wonder, even after this is perfected, whether if you go to a concert where the machines are on stage, but there's no one playing, you won't, and you have the experience of going to a concert where people are playing, you won't have that same sense of loss. Even though the sound may be equivalent. Not having the musicians there with their bodies showing you how to hear will make a big difference in how we hear.
Sounds like experimental philosophy.
So that is something that I'm also very interested in, and that's why I describe this sort of gray space that I think is existing right now, where it's either you listen to it online through your computer speakers or you go to a real concert. Will the experience of just seeing these ghostly instruments on stage be the same as listening to a real concert with people performing on stage be different? I think it will be, because so much of musical meaning is also communicated through the body of a musician, how they're playing it. A pianist, a violinist, they will move with the music, and I'm very aware of that. And it's not just an acoustic phenomenon. So will it be the same? I don't think so. Which is why I describe this interesting gray space of how close does it get to the real, to an actual real concert. And the reason that I phrase it that way is because, for example, when I go to a concert, I also know that sometimes I just close my eyes and listen. And in that moment, whatever's happening on stage actually doesn't matter. I'm just listening to the sound and listening to the sound as an acoustic phenomenon. And I wonder if in situations like that, if the person, let's say, is just kind of just spacing out, listening, closing their eyes and listening to it, will that make a difference? And also because, if I take an example from like the way we use Skype, back in the day, before Skype was a thing, I'm using Skype.
Back in the day for us.
Oh yeah, way back.
Back in the day before Skype was a thing, I think it was very difficult to imagine communicating with people that was not through like letters or telegrams, but then now communicating through people virtually with their faces appearing on the screen is considered is an accepted kind of substitute that, of course, is never the same as being with the real person, but it comes pretty close. And is accepted as sort of like a technological substitute to the person actually being there. And I wonder if the surrogate soundboards, once the system is perfected, where we'll stand in this gray space.
All kinds of technologies, we're surrounded by photography, which caused incredible conceptual and aesthetic and ontological questions at the time. So every time a new technology is invented, it creates complexity for aesthetics. And so this is just, aesthetics can handle this.
Mm.
This richness. It's not gray space; it's new space.
New space, yeah.
Right. I mean, I think there's just it's a new kind of way for music to exist or for art to be. And so I think.
And it's often the case that an innovation comes about in trying to replicate something that is available in some new way. And in doing so, it opens up new territory.
Yeah. So art is filled with this, the original manuscript, live performances, the original instruments, recordings of original instruments versus recordings of, prints,
all I'm
forgery, etc.
suggesting is that the goal of equivalent experience may well just drop out because the new experience has its own pleasures and challenges.
Mm-hmm. Yeah.
I just want, Franke program makes no conditions on anything. But if you don't give me an invitation, I don't have to pay for it. Give me an invitation to the first string quartet where this is done, I will be very upset. I want to be there.
Okay. Well, I mean, I
could
send
I want to
to
see
Yale.
it and remember it when. And if you need help making it happen, to talk to me too. But I think you're going to be in a place where it's very rich opportunities for making this happen. That'll be a new moment in the history of the arts, and I would love to be there.
Oh, thank you. Yes.
Sort of a stupid question, but it is also important where in the space in which you play the instrument. Right? Because I think where you play in Woolsey Hall or playing this room makes a huge difference.
True.
In that sense, it will never be, even the musical experience in itself will never be quite the same.
To clarify, the experience would be as though the violinist was playing for you in that concert hall that you were in. In the space. So there's no way that I can get Wolseley Hall to sound like, another concert hall. Well, you can, but that's not the
Just
purpose.
another tensor function, man.
stick it in there.
Solve it.
Once it's in the digital domain, I can tamper with the signal as much as I want. But yes, so it would be as though the person was performing live for you in the acoustic space that you were in.
So is that impossible though to mimic the effect of the space just with your instrument?
It is possible to simulate different spaces. This research is being done with speakers, so you can have the sound. You can have the sound be sent to you and with the right interference in a way that mimics different acoustic spaces. That's one of the reasons that things like surround sound and all these things work. In terms of having the signal coming out of the instrument in a way that would also mimic the acoustic space that it's in is a completely different beast, because that would also require me to know information on the space and be taking that information back in real time, figuring it out, and then having it come out here in real time, and knowing the information of this space, and then figuring out how to transfer that. It hasn't been done. It can be done, but it's a very complicated signal processing challenge. And that's an interesting question, because no one's. I haven't been thinking about it that far, but it would be interesting if you could do that.
If that's possible.
So we can make this room kind of sound like
That would be a
symphony hall in New York or something like that. That would be really cool. But yeah.
Well, thank you very much. And again, I know that Barbara and Rich are enjoying Arizona.
Here, it would require you to remove the entire string and then put two sensors back in back. The only instrument that they use more is for the cello. So, yes.
Interpreted differently, or is it's all trying to get at some sort of most accurate?
So the signal will.
I don't understand.
Yeah. So depending on where I stick this, the signal will always change.